talk about, XMM, the instrument observation modes, SAS, how it works, the different aspects of the mainly PN, MOS, and RTS, three of the instrument, we'll see later. Basic about the bad pixel detection, the good time intervals, and how to filter the data. Few words about the Swift detection, which I think is, is interesting because in XMM is important. Because we have a big field of view and we have a lot of scientific sources. In every observation, how to deal with SAS and the ODF, the CCF, how it works, and a few words about the archive, and how to download data. So XMM. It was launched in 1999, just before the 2000, because they wanted to skip the 2000 effect, and they wanted to put it in orbit before January 2000. So it's you will see later. The orbit was launched in an Ariane 5, which it was the biggest rocket in ESA. So thanks to that, we have a lot of fuel inside, and thanks to that, we are still operating. The orbit is very elliptical. It's 48 hours. You will see later. With the cameras, the three mirrors that we will see now in details. And in principle, we are in operational mode in the extended phase, and we have money until 2026 with a recommendation for 2027, 2029. And at this level, the member states, they meet every 2 years and decide how to continue with the mission operations. And in this case, they have cycles of 3 years. So in principle, we have the recommendation for 27, 29, and I hope it will be approved this year. So the orbit, as I say, it's very, it's very elliptical. Why? Because we are trying to get away of the radiation belts that are close to Earth, because these radiation belts affect the instruments, and we cannot observe during these periods. So with this elliptical orbit, we spend out of the 48 hours, around 40 hours at valid for observation, more or less. The apogee is almost 1/3 to the distance to the moon, so it's really far away. And nowadays it's funny because the orbit, this is how the orbit, the projection of the orbit on top of the Earth. So you see the typical loop of these 2 days orbit. And nowadays we are entering the radiation belts, not perpendicular, but a little bit. So it's difficult to escape from the radiation belt. So at the beginning of the revolution, when we start observing, we are suffering of radiation that is going and coming, and it's always a problem. So the spacecraft, it's a long tube, as you know, with 3 epic cameras. One is called MOS, and the other one is called PN. The field of view is 38 minutes for the 3 epic cameras, with an energy range between 0.15 and 15 kiloelectron volts. Then we have 2 gratings in 2 of the mirrors here. And this grating, disperse the light, half of the light to the spectrometer, to the RDS, which is the other instrument, with an energy range between 0.35 and 2.5 kiloelectron volt. We'll see later, a bit more in detail, the characteristic of each of these ones. And an optical monitor, similar to the one in Swift, that is observing at the same time together with the X-ray telescope. So here we have the mirrors, the 3 modules, and here we have the detectors. Do you have any question, please ask, because otherwise,
do you know what the inclination is? The orbital inclination.
I used to know, but it's highly, yeah, it's really highly integrated. Yeah. I can tell you. So the ground segment, what do we do on Earth? We have 2 centers, the Mission Operations Center that is at ESOC in Darmstadt, in Germany, and a Science Operations Center that is located in Madrid. At most, in the Mission Operations Center, they are in charge of the communication with the satellite. So they send all the commands to the satellite and the timeline. Then you have to bear in mind that XMM because it's no technology, but it was but it was in the 90s. We need contact, constant contact with Earth. So we don't have any memory on board, so whatever the satellite is observing, it has to be downlink immediately. So we always need an antenna listening to the spacecraft. So this, communication with the antenna is done by ESOC, Mission Operations Center, and we mainly use the antennas in Santiago, Chile, Kourou, Yataraga in Australia, and sometimes in Madrid, the one that we have in Madrid. And then at the mission, at the SOC, the Science Operations Center, we are mainly in charge of the science operation. We take care of the health of the instrument. It's a task that we do. At most in the Mission Operations Center, they only take care of the spacecraft, voltages, batteries, and these kind of things, and we check the health of the instruments at the SOC. We are in charge of the call of the proposal, and I hope you are all writing the proposal because the deadline is tomorrow. So I hope you have all submit the proposal. We also in charge of the instrument monitoring and the calibration, as I mentioned, the data processing, the SAS, the archive, and the dissemination of the data. And also, together with the community support, we have a help desk, and we are the interface with the community whenever they have any problem. The AO cycle that is finishing tomorrow. Once a year there is an open call. Scientists, can submit the proposal. We receive the proposal and we organize the TAC, the Time Allocation Committee. That is at the end, the group of people that select the proposal that will be accepted or not. Then there is a second phase for those proposals that are accepted, that the scientists have to, let's say, enhance the proposal that they send, basically how to operate the instrument. And they also, they do it together with the scientists at SOC. And also, we also provide feedback to the PIs. And then once the proposal is accepted, then at SOC, the mission planning and scheduling team, they check the priorities of each of the target, the TOs, that nowadays are more and more common. So we have more and more TOs, which means that we have to interrupt the timeline and include the TO, which means that we have to replan, every revolution every now and then. So at the end of the revolution, at the end of the scheduling, post is sent to the MOC, this planning file, and ADMOC is in charge of sending this command to the spacecraft. Just to mention about the scheduling and the mission planning, how important and critical it is, and now with the TOs that we have, this is a graph that I like a lot, which this is basically the visibility of XML in one revolution. We have the 48 hours in the x-axis, and here we have the sun, the anti-sun here, and the different planets, the moon here, and the Earth limb, which means that we can only observe in this very straight strip. So it's not, we have a lot of constraints, so not all the targets can be observed at the same time. And just for you to get an idea, this is the famous gravitational wave, event back in 2016. The XMM orbit and the regions, that we got from LIGO with the big uncertainty of the position of the source. So it was, at the end, it was somewhere here that we could observe.
What is anti-sun?
Sorry?
Anti-sun?
We cannot point either to the sun or to the anti-sun, because the panels, they always have to be pointing to the.
Same as Swift, we can't point at the anti-sun.
And basically, you need to have the panels always with certain orientation pointing toward the sun. So, the X-ray mirrors. We have 3 Volter telescopes, 58 nested mirrors, all co-aligned and all gold coated. Each of the mirrors, as you can see here, they have these spiders that maybe. There's one. There's one over there. This is so it's very nice. And we can see here how I guess you know how the X-ray works. I mean, the photons, I mean, basically enter into the tubes and they are deflected with this paraboloid, the hyperboloid figure of the mirror. So the X-rays are deflected and are pointed to the focal plane. So this is the schema of the single reflection and two reflection in the two layers. As I said, I mean, there is in two of the telescope there is a grating that deflects, I mean, half of the light to the RGS instrument, and the other half of the light goes directly to the MOS cameras. So PN, which is the other instrument that it only has one telescope for the instrument, is the one with the biggest perspective area. What else? The big cameras. We have two MOSES, each of which is this image here. Each of the MOSES with seven CCDs, and the two MOSES are orthogonal, one with respect to the other. The field of view is 30 minutes for both of them, and the size of the pixels is 600 by 600 and 40 millimeters per pixel in the case of MOS. PN, as I said, only one mirror for this instrument. 12 CCDs, trying to minimize the gap between the CCDs. The pixel size is a bit bigger than the MOS, but I mean, the readout is faster than the MOS one. You will see now the different observing modes, and you can, I mean, you read all the CCDs at the same time, quadrant by quadrant. The observing modes for PN. Full frame. I mean, there you have the characteristic, which is the time resolution, which is the important parameter, and the maximum count rate that you can get with this observing mode. This is the mode that you use whenever you have a bright source in the field of view. Camille will talk later about how to deal with bright sources in XMM. We will see. Large window, where not all the CCD is red, and the time resolution is a bit, better, 48 microseconds, and the count rate that you can achieve is a little higher. Small window where only the part of the central CCD4 is used, with a time resolution of 6 microseconds and a count rate of 130 counts per second. And then we enter into the timing modes. With the timing modes, we only use one CCD number 4, and we lost the spatial information because basically the readout is super fast. So the timing is 0.03 microseconds, and with a maximum count rate of 1,500. And burst, which is even faster. And you obviously you use this mode whenever you have a very bright source to observe. For the MOSES, we have the particularity. With MOS, you have the full frame, large window, small window, and timing. But you always observe, not like in the PN that for a timing mode you only observe with one CCD. With MOS, we always observe with the outer CCD. So the central CCD is the one that changes for the different modes. The full frame with 2.6 time resolution. In the large window, the central CCD, as you see, is read out only the central part. In a small window, just the tiny part of the center, but the rest of the CCD are in imaging mode. And in timing, also the CCD, we lost the spatial information, and the time resolution is 1.8 microseconds. And always the outer CCD operated, so which is good because you may have sources there. Then we move to the spectrometer, to the RGS. Okay, as I said, there are two of the Volter telescope. We have the grating, and the grating disperses the light following this dispersion equation, where we basically, knowing the incident angle and the dispersion angle, this beta, we know the wavelength of the event. The energy range that we cover in angstrom between 5 and 35 angstrom, And this region here is, is very rich in elements and transitions for low zeta elements. The field of view is more or less 2.4 arc minutes, so it's very small compared with the EPIC cameras. And we operate at the same time as the EPIC. So you can have, the high resolution spectrometry together with the EPIC cameras. We will see now how the dispersion equation works in detail. So this is an image of the CCD. We also have I forgot to add this to the presentation. In ArcGIS, we also have a small window mode. That is just we just write the central part of all the CCDs. Also for bright sources. So you have here the beta axis, the dispersion axis, where we measure the dispersion, the beta or the wavelength. We use the dispersion equation. And this is an example of two lines as we see in the CCD image of ArcGIS. So, few words about the OM. It's the optical monitor, 30 centimeters with a focal duration 12.7 focal, and similar to the one in Swift, with these characteristics about the bandwidth and the spectral, the field of view, the PSF. The time resolution, which is 0.5, and the different modes that we also have in OM. We have 5 consecutive windows that can observe the entire field of view. We also have a grism mode and the full frame mode that is good for surveys when there is a crowd field of view with a lot of stars, and 2 different modes in low resolution and high resolution with different pixel size for both those 2 modes and the grism. So at the end, when we talk about all these instruments, what are we talking about? The science as a projection, because basically the X-ray is a way to see all these different values in different projections. For example, if we collapse in time and space, we have the spectrum. If we collapse the information in time and energy, what we have is an image. And if we collapse in space and energy, what we have is a light curve. So and all those measures are indirectly related to the properties of the source that we are observing. So this plot here that I like a lot. This is just one observation of XMM, but in a kind of cube format where we have here the detector X, detector Y, the camera, and this is time. So in beams of I think is 100 seconds. So we see how all the events are coming toward the instrument, and if we collapse in this direction, in the time direction, we have the image. If we collapse in this direction, we have the light curve. And in this particular case, you see the source, which is this one, the source in the central part, and also you can see how. I guess I'm not sure. I didn't check it, but I guess this observation took place at the end of the revolution. And normally at the end of the revolution, when you are approaching to the Earth, you start having radiation from the radiation belt. So suddenly here you see how the observation start being noisy, and you have all this increase here in count rates, and it's just because it's noise. So now we have to deal with this and SAS to get some data. So what is the basic of the X-rays? Okay, we have detectors that are photon counting. So we have mirrors that, as we know, they affect the effective area, the PSF, the astrometry, the vignetting. We have the filters that also affect the effective area, the CCDs that introduce the quantum efficient, the CPI, the distribution, gain, and also the electronics that it also affect to all this information. So what we are trying to get out of all this the data is the information of the X-ray events that we call it. I mean, yes, the events, no, which give us information about the imaging, where the events come from, the effective area, how many events we have, the redistribution, the effect of these photons, gain and CTA, which are the events that we want to use, the timing, where they arrive, and the background, if it is part of the source or not. So we have to deal with all this information. And then we jump into SAS, which is the software that we use to analyze all this data. So SAS is a suite of binaries tasks that are able to analyze all the XMM instruments. It was written in C++ and Fortran 90, and we have Perl and Python, a lot of scripting languages also inside. Mainly the Perl and Python is used to create what we call meta tasks, so tasks that calls another task. We use, the public libraries, as you probably know, like Swift-XMM, Grace, and DS9. Although now that we are moving toward these cloud environments, we are shifting, changing a little bit the way we deal with these libraries. It was developed by more than 30 programmers around the world in 6 different countries. And it was a challenge back in 1998, 1997, how to work with these distributed, people where we didn't have the tool that we have now for it. So also, in SAS, we, at the same time that we receive the data, we run what we call the pipeline, the PPS, the pipeline processing system. And this pipeline is able to run all these SAS tasks with some default parameters to get the scientific products. We get the images, spectra, and light groups, probably the sort of all of the sources in the field of view. I will mention it. At the end when we talk about the archives, I will mention a little bit about the PPS. So we currently have, released SAS 22.1, beginning of the year, and the idea is to release a new version next year. And I brought this X because our aim is to release the source code that we stopped releasing many years ago because of proprietary rights. And now we are trying to get rid of all these proprietary rights from the source code. And if we manage to get the license from ESA, we will release SAS 23, but it will be 22.1 without the proprietary code. So it's going to be the same functionalities. And then we will probably release 24 in 2026. Depends on if we get the license or not. So, and what can we do with SAS? Everything, because as I said, we analyze all the instruments with the same software. So we have here the XMM. We get the data, and the very first thing that we do is construct what we call the ODF, which is observable data files. And this ODF contains all the files that you will need to later on process the data. Together with the ODF, we add some calibration information that we got, now after the revolution is taking place, and the corrected attitude from mock. We add those two files to the ODF, so then we have the real ODF, that is the one that we distribute to the PIs, to the scientists. And with this ODF, we can extract, extracting the products with the calibration and the CCF file that we will see now. We get the product analysis, so we can construct the exposure map and the PSA, the effective area, the images, the light group, everything. And at the end, you can do your science because you get the final product. In terms of what does it mean in terms of SAS? But we have two main branches, what we call the EPIC branch and the RGS branch. OM has its own branch as well. But OM has one particularity, and it's OM with the OM chain task that we have. It does everything in a row. So it creates the images, automatically everything, without having to tune many things. So in the Epic branch, which is the branch that process the MOS and PM cameras, the main tasks that we will see now are EM-proc or EP-proc, or EM chain or EP chain. We have to, for historical reasons, the EM chain and EM-proc, it does the same, and EM-proc and EP chain, it does the same. One is in Perl, and the other one is in C++. So it's the only difference. And with these procs, we get the event file, the event list, and with the event list, we can start creating the spectra, time series, images, or the subdetection. So the event list is the level one, product, and is the events, the calibrated events, and with those files you can start creating your products. And then you have to write your paper, and then you are finished. In the RGS branch is what we have is RGS-proc. In this case, we only have one RGS-proc. And RGS-proc is similar to OM. It does a lot of things. You will see later. It creates the event files as well as in the Epic branch, but at the same time, it also creates the spectra and the shortlist, and the time series. You may ask why. In RGS, as you know, because we mainly only have one source because the detector is smaller. And the region to extract the spectra is more or less always the same. You get also always the same region. You can go further and get, the spectra and the light curve. Nevertheless, you can always tune and optimize your region for your source. We'll see a bit more in detail these two branches. So at the end, what is the aim of SAS? Just apply all the calibrations. As you can see here on the left, you see an image without the raw image, without any calibration. And on the right, you see is the same image with all the calibration applies and the screen and the filters to get something that you can really use. So that's what SAS is supposed to do. And it does. A little bit more in detail, the proc chain, just for you to get an idea that all what we call meta task is a set of several tasks that at the end create the event file. In the case of EpiProc, you have all these tasks here that, for example, if you read the documentation, if you frame, is the task that it creates, from the raw event files, the frames where those events come from. Bad pics and bad pics fine, as the names suggest, are the one in charge of detecting the bad pixels in the image. If events, process the events and get the energy or compute the energy for all the events. AdCalc calculates the astrometry for the events, and then EVELIS combine all these different intermediate files that are created during all this process to create the final event list. Bad pixel, just few words. In principle, you don't have to worry about the bad pixel. It does, automatically, but we have three different bad pixel levels: the ones that are rejected on board, the ones that are marked as bad in some calibration files, and the ones that are detected during the execution. Because sometimes you have bright pixel that suddenly appears or bad pixels. So it's all these, computation are done automatically, and the information is also stored in the event file in case you want to check and see what is going on. The data filtering, just a few words. It also, the procs does a default filtering for all the images and remove, whatever it considers as bad events or bad, time intervals. You can enable or disable this functionality with parameters. In this case, for the Epic, the flag filter events, but it's always true by default, and you don't have to touch it. I mean, for you to get an idea how important the filtering is, and you will have to filter always the data you will get. Here you have an image. This is the output of the EpiProc in this case for an epic image, and you see, I mean, you can see the check gaps and some bad columns that have been removed. So the very first thing that you have to check, as you also see in the image that we see this cube, this 3D image, you may have, I mean, flaring periods. I mean, periods in your observation where the sun or whatever have more radiation, and you want to get rid of these periods here, because at the end you don't see your source. So to do this, we will see later in the hands-on session how to filter those events. You create this light curve. You select what is the threshold that we recommend for PM to cut in the 0 point counts per second. You will see it in the documentation. And then when you create this good time interval, which is only considering the period where you have 0.4 counts per second, you get your clean event file. So you will see it in this afternoon with the threads how to deal with that. As I said, ArcGIS, it does all the filtering automatically, but nevertheless, it's always good to have a look to the ArcGIS light curve, because you may have to remove some flary periods. To get an epic PN spectra, just few words. Now with SAS in data labs, it's a bit different, but the concept is the same. I mean, if you use SAS in your laptop or in data labs, you have to do the same, but with different tools. We have a task which is called XMM Select that you can use if you use SAS in your laptop. In data lab, it's a bit different. You will see the thread, you will follow the threads, and you know how to deal with that. This is the GUI of XMM Select, and it allows you to do a lot of things. Create images with different coordinates. You can create light curve, spectra, histograms. Basically, you can filter, you can do almost everything. And the idea is to create a spectra. You have to select the region where your source is, and the background region, and then call magic tasks that create the spectra responses, which in this case is expected, or you can do it step by step. Although this example, and you get the spectra. This example is using XML Select and DS9. This afternoon, and during the hands-on session, if we use data labs, we will do exactly the same, but instead of using DS9, we'll use GS9, which is a JavaScript version of DS9 that we can use in a browser. That's it. Always, worth to mention the regionalized task that optimize the centroid of your subregion and the extraction region. With the optimizing the signal to noise that you can do automatically. You call this task, you get the regions, the optimized regions. Again, this afternoon with data lab, it's a bit different, but the concept is the same: region, background region, and get the spectrum. But for ArcGIS, just few words. It's similar to the Epic branch, but as I said, we also get the spectra and the responses in the same execution together with the flags. So a spectra in energy units, the flag spectra and the shortlist. You can also filter or inspect the ArcGIS event list with XML Select, and you can also play with the different. You can plot different coordinates. You can plot the cross dispersion with the against wavelength, the beta with cross dispersion, all the images that we will see now. And why do we have to? I think it was mentioned in this slide here. that is the coordinates. I mean, it's important that you have to use the coordinates when you run RDS proc, and we'll see why. You may have your source with your RDS detector, as you can see here, that is not pointing directly to your source, but it's pointing to where the spacecraft was pointing at, no? And your source is here. So this, because we know the dispersion equation, that it depends on the incident angle and the dispersion angle, we need to take into account this angular offset in the dispersion direction to correct the wavelength with respect to the spacecraft on axis attitude. So at the end, we have this angular offset that is a function of the coordinates and the pointing, the target coordinates and the pointing coordinates. So we always have to enter the coordinates whenever we want to run RDS proc, because as you can see here, I mean, we will have 1 arc-second, I mean, misalignment is around 2.3 milliangstrom. So wavelength scale is not correct. So we will see how to run RDS proc with the coordinates. What RDS does? A lot of things. This is a similar slide as the one that we have for PM with all the individual tasks that RDS proc have to execute to get the final products. As we say here, there are some tasks that are source independent. It doesn't matter where the source is where you calculate the frames, the energy, the bad pixels, and the attitude. And then there are other tasks that they are source dependent. So we need to know the coordinates of the source, I mean, to optimize the execution of these tasks, which are RDS angles, filter regions, RDS spectrum, and RDS RMFGen, which is the response matrix generation. Nevertheless, if you run RDS proc and you don't enter your target coordinates, RDS proc assume that the coordinates is the pointing coordinates, and you always get something. So you can always, if you are, I mean, learning or you want to respect the result, the products, and the spectra and everything, and then you are not going to publish a paper, you can always run RDS proc and you get something, although not that accurate as it should be. What I said, I mean, RDS proc, it does basically everything. So you get the images, you get the spectra, you get the response matrix, and you get even the spectrum in energy unit with the RDS fluxer. Here you have an image of RDS in lambda and cross dispersion, and this is an image of lambda and energy. This is the typical, what we call it, this banana plot, where we have the first order, the second order, and the calibration lamps that you can see here, the calibration lamps in the image, which are those plots here, the banana plot and the cross dispersion plot. And here you see that, as I mentioned before, normally the extraction region to create the spectra is always, I mean, I think it's defined by default 95% of the energy of the central part. So unless you want to change this region here, that you can, you always use the same. Question? There's something. Now this boring. Come on, keep going. So a few words about the source detection. We also, I mean, have the SAS. We have the task to create, I mean, to analyze the image to get all the sources in the field of view. That at the end we are trying to get the fluctuation in a small, I mean, distribution. No? This is an image of all the sources detected in one observation, with the goal to maximize the source detection, minimizing the effect, the spurious sources. Maximizing and minimizing the maximum the signal to noise. We have to use different energy bands. We have to define threshold, create GPIs, or we need to have the event files as clean as possible to at the end, execute this task, which is called EAT exchange, that it does everything. You need to enter to these tasks and the images, the energy bands, the event files, clean, it automatically, run all these tasks, epoch detect, display map, EML detect to get the final shortlist that is useful. The pipeline execute this source detection by default, so you can always go to the archive and check how many sources you had in your observation. Now, SAS, the installation. This is SAS 22 that we released this year for Ubuntu 22, Ubuntu 24, not 22, and Red Hat 8. We also distribute, for Mac, but Intel chip for Ventura and Sonoma. And we are having troubles to get SAS built in Silicon processor, mainly because of the Fortran compiler. So we are trying to get it, and we have to get it, but we still don't have it. Nevertheless, you can run the Intel binaries in the Silicon processor using Rosetta, which is a conversion tool that Mac have to execute Intel binaries in this machine. And also, and we have the SAS in the cloud environment, and we are now also offering SAS in Docker images. That we also encourage the people, the user, to use it because Docker image. We also released in the past a virtual machine with everything installed inside, but at the end you have to distribute 20 gigabytes of, with all the virtual machine there, which is a lot. And now with the Docker technology, the image is a bit smaller. You have everything inside, and if you know a little bit of Docker, you can execute it as if it were a virtual machine. So I think it's a good solution. And we have to go in this direction because nowadays it's everything Docker, Kubernetes, whatever. So the installation, in case you want to install it in your laptop, is straightforward. It's not too complicated. For SAS22, we changed a little bit the nomenclature of the file that we were distributing because we wanted to enter the Git commit. This is the commit that we use to create this release. So if you go to Bitbucket, you download this Git and you have the SAS as it was released. The date, that is something that we use in the past and we keep it, the operating system and the GCC version and the architecture. That is only Intel architecture. I hope it will be also ARM in the future. You enter the file, you click on the install, there is a install script, and it does everything for you. You only need to define the Perl and the Python places, and that's the thing. And then to run SAS, we need hash-off is something that we are trying to get rid of. It's not that we don't like hash-off, but it's something that it's a very big software for us. So we are trying to, if someone wants to use hash-off, fine, use hash-off. If you want to use SAS, use SAS. But we have few tasks that use, hash-off tools. Okay. So you define hash-off, you define the directory where the SAS is installed with this environment variable SAS dir, and then execute the set SAS. We have both in bash and in C#. And with this, in principle, you are done. You can use SAS. Two important things that we need in SAS. One thing is the calibration files. So every observation, before it can be processed, it needs what we call the calibration index file. And the calibration index file that is created with this task build, it searches in all the calibration files that you have. You have to previously download and have it in your computer. All the calibration files that you need. So the build will see later check the date of your observation and check what are the CCF that have to be used for this particular observation for this particular time. before we run TPIL, we always have to tell SAS where the data is. So the SAS ODF is the very first thing you have to do. I mean, you download the ODF, you put it somewhere, and you define SAS ODF because, okay, that is where I have the data. And the build creates a feed file with all the calibration file, the version, and the version you can always go to this file and check what is the version you are using in case you need it. But by default, it always uses the best calibration files, so you don't have to worry about it. And once the build is executed, you define as CCF this variable, and then you can pass to the second step, which is the ODF ingest, which is a task that it creates this advanced summary file, which is an ASCII file that contains a lot of information about the observation you're dealing with: filters, housekeeping data, voltages, things that are extracted from the housekeeping files and put it in this ASCII file. Because you previously defined this as ODF because you have to run TPIL. I mean, this variable is already set. You run ODF ingest, and then you have this ASCII file with, I mean, a lot of information about each exposure and filters, calibration, everything. And that I mean, the task uses later. You always need this file. And then you set SAS ODF to the summary file, and it's done. And then you can start executing all the tasks. This ODF browser, I mean, I like it a lot, although I don't know if people use it, but it's nice because it gives you an overview of your observation. I mean, the exposures you have, because you may, although you ask for an exposure in your proposal for whatever reason in real time, there was a problem and the exposure had to be stopped and restarted or rescheduled. And here you see all the exposures of your observation in OM, PN, and yes. For example, in this case, in PN there were 3 exposures, probably because there were some problems in real time, and they have to stop, start, and only 1 exposure for RGS and 2 for Moses. It's nice. In the data lab, we cannot see this ODF browser, but well, you will see it. The TPIL, just only to mention that it always by default, when in all the calibration files, we have this val date, eval date, and date. So which means when those files were valid. So TPIL, it takes your observation, where the observation was performed, goes to these keywords in the CCF and select the calibration file that has to be used for this particular observation that it was taken at this particular time. So it does everything for you. Which means that if you are analyzing a very old observation, you may use a very old calibration file, but because it was the one that has to be used. The basic step to start working with SAS. You define your SAS directory, you execute the set SAS command, and it's done. And as I said before, you run build, run ODF ingest, and then you have everything ready. And we have 1 version for the CCL and 1 version for the bus. You have to change. So it's the same, but with the sport. You can have this as a reminder in case you have to use it. Now, documentation about SAS. We have everything on the web. I mean, you go to the Cosmos web from for XMM, and you have all the analysis thread that we will see this afternoon, the documentation, the online documentation, the watch out page that is important because sometimes when after a release we realize that there was a problem with whatever, and then you go here and check if there is any watch out because maybe someone found the problem and we already fixed it. And also, but I forgot to mention SAS. SAS is the extended source analysis software that is part of SAS, and you can use in case you want to analyze extended sources. It's important, and the threads are completely not completely different, but the way to analyze this extended source is a bit different. So we have all the information that you can get there. The documentation, in particular the threads that we'll see this afternoon. We have some Jupyter notebook that to help the user to start analyzing SAS. We will use those threads this afternoon during the hands-on session in Data Lab, but you can always download the Jupyter notebook, run a Jupyter server in your desktop, and do it locally. So you have to use Data Lab; it's not mandatory. And we also have the threads in HTML format, which means that you can go to all these threads and check. If you want to extract or correct for out-of-time events, for example, these out-of-time events, you go to this thread here and you see step by step the task that you have to execute to correct for this particular, in this case, effect, not these out-of-time events. And we also have the threads for RGS and for 2 words about the archive. So I guess you all have visited the XMM archive. You have to register, and when you are registered, you can select your source, source ID, target, coordinates, everything. You get this panel here, and in this panel, you can see the pipeline product. So because once the observation is taken, the very first thing that we do at SOC, we run the pipeline, and we deliver the ODF to the PI, and as soon as the pipeline products are processed, we also send it to the archive. I don't know if you know that, the data is proprietary for 1 year, so the PI can access to this data for 1 year in private mode, and after 1 year is public. But so you can go here and check, the observation, if it was, you can read also the report from the PPS in case there was some problem, or the screening they found some problems, everything. You have to go to the archive first, and check your data. And the ESA Sky, that is I always like to mention, you can access the ESA Sky via the archive with this button here, and it redirects you to the ESA Sky. That is a cool tool to play and check out the the sky in X-rays, or compare X-ray with the optical. You can visualize. A lot of missions data is really cool. Just to finish, things that you need to take into account whenever you have an XMM observation. So it's always good to have a look to the PPS before you start working with your data, to check if there was any problem or whatever. Check the calibration files, the validation. If there are new validation report, new calibration release notes, it's always good to have a look to know if we release something new. You compare your calibration with the latest available, as I said, and then go to SAS and check if there is a new version, or there is a watch out, a patch, or whatever, and use it. And if not, you can always help the help desk, XMM help, Cosmos, SINT, and send us. And that's. Thank you. Not this afternoon with the hands-on session.
Yeah. If someone online has any urgent question. No. So then I think we can go to Natalie.